So one of the most common errors for this one, calcium carbonate, I did this one on the board in class, so I'm not going to redo it. But H2SO4, H2SO4, does it ionize both hydrogens at the same time or one at a time? It ionizes one at a time, so if we take off the first hydrogen, then we're left with H plus and HSO4 minus. Now, is HSO4 minus a strong acid? No, HSO4 minus bisulfate is a weak acid, so we just leave it alone. And so one of the most common errors that I see for this is that people will ionize both hydrogens at the same time. But both hydrogens don't come off. It comes off one at a time. But you might have seen something that looks conflicting to this. And it has to do with this half reaction here. If we look at it, it's sulfate plus 4 H pluses. So it looks like all the H pluses have broken off from the sulfate, but that's not the case. They write it this way because it's any mixture of acid and sulfate. And so if this were sulfuric acid, then we'd have bisulfate. But we could make this mixture other ways. So for example, if we took sodium sulfate and hydrochloric acid, we'll get the same mixture. You know, sodium sulfate and hydrochloric acid. But it doesn't matter in redox if this is bisulfate or even sulfuric acid, because in bisulfate, the oxidation state on sulfur is exactly the same, and in sulfuric acid, it's exactly the same. So sulfuric acid, bisulfate, and sulfate react the same in redox reactions. And they react the same because the sulfur is +6 in all three of those species. That's redox. In acid-base, it makes a huge difference. So for acid-base reactions, we need to know, are we dealing with H2SO4, bisulfate, or sulfate? They're totally different acid-base properties, but they're the same, or treated the same, in redox. Is that clear? So we don't break off both. The other common error with this is carbonic acid. You can't leave carbonic acid. Carbonic acid is inherently unstable, so you can't leave it in any of the three equations. So what a lot of people do is they'll write carbonic acid in equation 1, and then in equation 2, the ionic equation, they'll write CO2 and H2O. But no, it's got to be CO2 and H2O in all three equations. The complete equation, the ionic equation, and the net ionic equation. So that's all I'm going to say about that first one. The second reaction, potassium fluoride and acetic acid. I write acetic acid like this for double replacement reactions. I know in our chart it's written differently. It's written as a condensed structural formula. The reason I write it the other way is because this is a BA. You know, the cation is H here and the anion is acetate here. And so I'd rather leave it in AB form. But when we do the condensed structural, the acidic hydrogens usually, or the cations usually at the end here. And so just a matter of convention, if I have potassium acetate, the way we write potassium acetate in condensed structural form is not with potassium first. You know, when we do that type of form, it's written a little differently. Oops, this is the wrong one. And so this is going to yield what? Yeah. So this is how potassium acetate's written in condensed structural form. Cation at the end. Plus hydrofluoric acid. All these are aqueous, so you have a choice. You can write aqueous for all 4 of these species or leave it off for all 4. Don't write it just for the first 2 and leave it off for the second 2. I'll have to take a deduction. So some people said this is a weak acid and this is a weak acid. So we're going from weak acid to weak acid, and so there's no driving force. But that's not the case. What we're going from is WA to SA. What does W stand for here? Weaker. It's all relative. And then S, stronger. HF is not a strong acid, but it just has to be stronger than acetic, which it is. And so HF is a stronger acid than acetic. You can see it here. It's a weak acid, but it is stronger than acetic. So I'd like you to show me why there's no driving force. We're going from weaker to stronger. And so there's no driving force, basically. You know, in other words, we're going uphill in this particular reaction. And the downhill direction is the reverse. So the reverse reaction is favorable, the forward reaction is not favorable. Here. Some people leave this blank here and just write NR. If you write NR, you know, it's correct, but you should show more. I mean, why is it NR? You know, so you should show more analysis. It's NR because we're going from weaker to stronger, and it's not a driving force. But sometimes what people do is they screw up the driving force. They think it's an NR, but there's actually a reaction. On the test, to maximize your chance for partial credit, you know, you may want to write it all out. That is, if you just write NR and leave everything else blank, then you aren't going to get much partial credit if you get that driving force wrong. And so if we do this, we could write out the ionic equation. Does potassium fluoride ionize? Yes, it does, because it's a soluble salt, strong electrolyte. Does acetic acid ionize? So this was another mistake that I saw. Does acetic acid ionize? Some people ionized it, but you shouldn't ionize it because, why? It's a weak acid. Potassium acetate, do we ionize that? Yes. Hydrofluoric acid, do we ionize that? No. So some people ended up ionizing the whole thing, and then all the ions canceled out. And they got no reaction because everything canceled out. That's not the case. It's incorrect. Okay. But anyway, this is NR, weaker acid to stronger acid. You have to show me what the weaker acid is and what the stronger acid is. Sometimes people just write it on the side but don't point out which is which. You have to explain it. Lead 2 iodide plus hydrochloric acid. Yields what? Lead 2 iodide's a solid. It's insoluble. Hydrochloric acid is aqueous. Lead 2 iodide and chloride, these are both insoluble. And hydroiodic acid is. So one thing we could say is that both are strong acids. And what do we know about strong acids as far as their ranking goes in the acid chart? They're equal, yeah. So the 7 common strong acids here are equal in water. They all ionize 100% or hydrolyze 100% to produce H plus or hydronium. And so if I have 1 mole of any of these, they all produce the same amount of hydronium, so they all have the same acid strength. Except for H2SO4. H2SO4 produces a little bit more hydronium than the others because it's a diprotic, but not twice as much. It's less than twice as much because HSO4 minus bisulfate is a weak acid. All right, so these are equal. Now the weak acids vary in strength. So we'll have a spectrum of acid strengths here. The higher we go up, the more hydrolysis we have, the more hydronium we produce. The lower we go, the less hydrolysis we have and the less hydronium we produce. And so these will be ranked. And so going from a strong acid to a strong acid is not a driving force because of the leveling effect. Some people wrote no reaction. How do you know that there's no reaction? How do you know there's no driving force? So for example, if you have lead chloride, that's a precipitate. So isn't precipitation a driving force here? And it turns out it might be or might not be. Why? Because this type of reaction is called a solid to solid. Solid to solid transformation or solid to solid reaction. And it depends on which solid's more stable. If the chloride's more stable, it's downhill. If the iodide's more stable, then it's uphill. You know, the downhill direction would be the reverse. And so how could you tell which one's more stable? Oxidation state of lead didn't change. It's +2 in both. Well, how else could you tell which one's more stable? Is there a chart of precipitates that tells you? No, we don't have a chart of precipitates. And so this type of problem wouldn't have been given in Chem 4 because it's too complicated. And so what you could say is, you could say that in order to determine whether there's a reaction or not, we need more information. So solid to solid transformations require more info. But as I mentioned before, you know, on tests, or if somebody's asking you a question, you should try to answer it. And so we could try to answer it, you know. There's two ways we could try to answer it. One way is by solubility. The one that's less soluble is more stable because what happens is when you dissolve these crystals in water, the water tries to break them apart. And the more soluble it is, the more broken apart it gets and the more you can dissolve in water. That's one way. And then we can look up the solubilities. Where can we find the solubilities? What book? Is there a book that has those in there? What book was that? Did I ask you that before? What was that book? Merck Index is good. We can look at there.
What the question was for real?
Yeah.
It just came to my mind. That's kind of crazy.
All right. Merck Index is one. What's another one? The big, well, they change the color every year. CR, did I talk about this? Yeah. CRC or Wikipedia. We could do that, but you can't do that on a test. So what you could do is you could try this from a more theoretical perspective. From a more theoretical perspective, let's look at the bond holding lead ions and iodide ions together. So if we have lead, that's a 2+ ion there, and then we have iodide. Which one's bigger, iodide or chloride? Iodide's bigger. And the charge on iodide is -1. And so we'll throw a lead ion here and then a chloride. Chloride is going to be smaller. So iodide, I don't know if it looks it, but it's bigger. It's supposed to be bigger. Maybe I should draw it. So if I try to pull the iodide off lead, or to separate these, which one will be easier to separate? So we could use Coulomb's law. Coulomb's law says the force of attraction or repulsion is proportional to the charge on the cation times the charge on the anion divided by d squared. D is the distance between the center of charges, so it's kind of weird because the charges, the ions are actually touching one another, and so there's no distance between, but there is a distance between the center. So that would be the D there. So if you look at the distance, the chloride is going to be closer. At least the center of it's going to be closer. And therefore, it should have a stronger force of attraction. And therefore, it should be harder to remove or easier to remove. It's going to be harder to remove. The whole thing with Coulomb's law, the way I like to think about Coulomb's law is by something called charge density. And so the way I think about it is the more concentrated the charge, the stronger the interaction is. So if we have a -1 charge distributed over this volume, I'm going to have a -1 charge spread out over the entire volume here. Whereas over here, I'm going to have a -1 charge, but it's going to be more concentrated. Into a smaller volume. So chloride has a higher charge density than iodide. Iodide's charge density is lower. And so which one should have a stronger interaction? The one with the higher charge density should. So when we use Coulomb's law like this, and when we visualize bonding like this, then we're making an assumption. We're assuming 100% ionic bonds. But with heavy metals like this, there's a covalent, certain percentage of covalent interaction there. Furthermore, we have to look at other interactions. Because once we break these ions apart, then these ions have to be accommodated by water molecules. And so to accommodate ions, for water molecules to accommodate ions, what is easier to accommodate, small ions or big ions, if you're going to fit those between water molecules? Small, because you don't have to break as many water molecules apart. So smaller ions and smaller molecules are more easily accommodated by water molecules. And so there are multiple factors, but if we only assume one factor, just the strength of an ionic bond, then we'd expect PbCl2 to be more stable. And so I expect a driving force here, because PbI2 going to PbCl2, it should be a stronger lattice. And so if that's the case, then we do have a driving force. That's my analysis. This is my theoretical analysis of the first approximation. But what we should do is we should verify this experimentally, because if there's ever a conflict, let's say there's a conflict between theory and experiment, do you know who wins? Does theory win or does experiment win? Experiment always wins, because experiment is just usually factual observations. So that means the theory probably is missing something or it's wrong. So, this is like initially when the COVID outbreak happened, they had some theoretical models about how rapidly it was going to spread across the world. But fortunately, those theoretical models were wrong. Otherwise, it was really grim, the outlook there. But that's a case where, okay, the theory was wrong, not the factual observations. The observations were spread much slower. So let's take a look. Here. I wasn't supposed to bring that one up. So we'll take a look at lead chloride. So what we're trying to do is we're trying to tear apart the lattice, and that's what's going to happen when it dissolves. The ionic lattice is going to be broken apart. When we take a look at the solubility in water here, solubility in water is 0.99 grams, almost 1 gram in 100 milliliters. 1 gram in 100 milliliters, does that sound all that insoluble? No, it's a whole gram in 100 milliliters. 100 milliliters isn't all that much water. And you can put a whole gram's worth of lead-2 chloride. But when we look at the criteria for solubility is 0.1 molar. And so that's less than 0.1 molar. Lead's really heavy. The molar mass of this salt is 278. It's pretty heavy. And so about a gram per 100 milliliters at 20 degrees C. Okay, let's compare that to lead-2 iodide here. This is lead-2 iodide, nice yellow crystals, orange crystals. So we'll compare it at 20 degrees C, 0.76 grams per liter. 0.76 grams per liter means 0.076 grams per 100 milliliters. So we got 0.08 versus 1. And so it turns out lead 2 iodide is a lot less soluble. So this first approximation was not good. This is wrong. And so it means that we need to factor in other things like covalent. You know, we have a range of bonds from covalent to ionic, and in between would be called polar covalent. You know, but we have a range, and so the bonding probably isn't 100% ionic, especially with heavy metals like this. This is why some heavy metals are not strong electrolytes. Some heavy metal salts, even if they're soluble. Some heavy metal salts are weak electrolytes. But based on that observation, it turns out that this is more stable. And we got that because it's less soluble. More stable in water. And so indeed there was no reaction, but you have to explain why. For a test, though, you wouldn't. A test, you could just say this particular one requires more info. But let's say you're wrong. You should have known the info. Then what you could do is you could complete this. You know, to try to maximize your chance of getting partial credit, we could do the CE, which was above, and then the IE. The IE, PbI2 is an insoluble salt. And then what about HCl? Strong acids. Strong acids ionize completely. I noticed that some people don't balance it. They had 2 HCl's up there, and then they've only put 1 H plus and 1 Cl. Everything has to balance. Not only that, some people forgot the charge. Don't forget the charge on the ions. You need to make sure you incorporate those. One of these things that I always wonder about is that some people mess up the charges on things like fluoride. You know, once in a while I'll see somebody write fluoride with a -2 charge. Where do they get fluoride with a -2? It's only 1 electron short of neon. You know, fluorine has 9 electrons, neon has 10 electrons. How can you get a -2 charge on fluorine? Not only that, on that particular test, I gave this sheet out. You know, the sheet out has all these charges are correct. And so you could have just looked it up on the sheet. It was given on the test. Also, on the same test, somebody got carbonate wrong. They wrote carbonate with a 1- charge, not a 2- charge, like it's shown on the sheet. So I could have told them to look at the sheet. The answer is there, but the problem is on exam 2, if you get the formula wrong, I can't give you credit for the rest because, and so that's like right at the start. So you just earn the minimum amount of partial credit, if any. You know, so you got to get the formula correct on exam 2. It's important. But you have some aids like this. And so this sheet I'm going to give for the test as well as the periodic table. But it's still useful to have these memorized, you know. And so as an exercise, we did this already. The exercise was read the names of all the oxidizers. Okay, we did that. And most of the reducers we did. Can you name all these? Probably not, like this one. This one we learned how to name in Chem 1B. This one's organic. You know how to name this in organic chemistry. This is trichloroacetic acid. The 7 common, those should be easy. Hydronium's easy. But the rest of these and these should be easy too. Still, I throw in amide on the test, and a lot of people don't even know what amide is and leave it blank. Methide is so rare, I'm not going to throw methide in there. In fact, I didn't even talk about methide, but methide's the strongest base on this chart. If you look in the classroom chart, amide, or actually not our classroom is missing. If you look in the other classrooms charts, amide is the strongest base on the chart. All these bases here are negligible. They're so weak. We don't really consider them bases. So for example, like chloride, let's say you ran out of antacid. Antacid would be like one of these weaker bases like carbonate or bicarbonate or something like that. And instead you tried to neutralize some stomach acid with sodium chloride. Is it going to be very effective? Well, you said, I see chloride here on the base chart, so it's probably going to be effective at neutralizing stomach acid. Well, it's not, because these ones up here are so weak, we don't even consider them basic. All right, so HCl is a strong acid, and then we're going to go to PbCl2, which is an insoluble solid. And then hydroiodic acid is a strong acid. We have that. And then the NIE for this would be PbI2, solid plus 2 chlorides. It's PbCl2, solid plus 2 iodides. The NIE. Don't forget the charge. Next one here, magnesium nitrate plus aqueous ammonia. We treat aqueous ammonia as if it were what? Yeah, we treat it as if it were ammonium. What?
And hydroxide?
Yeah, ammonium hydroxide. But don't write ammonium hydroxide here, because if you go by, or if you try to go by ammonium hydroxide, you're only going to be able to get less than 1% ammonium hydroxide. The purity. It'd be 99% ammonia, less than 1% ammonium hydroxide. And in these equations, we want to write the major species. We're not writing the minor species. So if you wrote ammonium hydroxide, you're writing the minor species. You're correct. Ammonium hydroxide does react, but you're not going to be able to go and pull a bottle of ammonium hydroxide off the shelf. Actually, you might be able to. We have an old bottle here labeled ammonium hydroxide. The old bottles are still labeled ammonium hydroxide. The new bottles are just labeled aqueous ammonia. Because it's 99+% ammonia. Less than 1% ammonium hydroxide. So you might go buy a bottle of ammonium hydroxide at the store and then return it because, hey, it's only less than 1% ammonium hydroxide. I was expecting 100% ammonium hydroxide.
Sorry, what store would you buy that at?
What store would you buy it at?
Yes.
At the chemical store.
Oh. I would assume those are mostly online.
There's chemical stores. There's
Really? Like in person?
yeah, there's Spectrum Chemical is in Gardena. You can go, if you set up an account, you can go buy chemicals there. There's some place in, I think, Lawndale. They have a bunch of chem supplies and a small amount of chemicals that cater to the home chemist, you know.
There's a lot of home chemists in Gardena.
Probably. Yeah. I saw this house, you know. I was just curious. There's this open house, and this guy used to work at TRW or one of the aerospace companies, and he had in the garage he had a hood like this, and on the side, the side of his garage was just filled with all different kinds of chemicals, reagents. And then I was thinking, where is the hood vented? The hood is just vented through the roof, and so I was like thinking about the neighbors there, you know. They're breathing in all these chemicals. Yeah, it was pretty crazy. I mean, you know. But anyway, this is the most common error. The most common error will be people put ammonium hydroxide here. You shouldn't put ammonium hydroxide because we want the major species, not the minor species there. All right, then nitrate salts are all soluble, and so this is a strong electrolyte. This is going to make Mg2 plus 2 nitrates. And then ammonia is a weak, so leave it alone. Water is a non, so leave that alone. Magnesium hydroxide is insoluble, so leave that alone. And make sure you get the ratio correct. It's 2 ammoniums, and the ammonium has a positive charge, and it's 4 hydrogens and 2 nitrates. So a lot of people miss the charge or didn't get the correct ratio. For example, they might have had 2 ammonium nitrates here, but only put 1 ammonium and 1 nitrate down here. So that was another error. And then the spectator here is just nitrate. And so the net ionic equation will be magnesium 2 plus 2 ammonias plus 2 waters yields magnesium hydroxide and 2 ammoniums. Now, you could write, okay, the driving force for this is precipitate, but I don't want to read it over here. I want you to show me what precipitates. So you could just draw an arrow and just say dia precipitate, you know, something like that. The reason is because sometimes I see like people do stronger acid to weaker acid, and they're pointing at the wrong thing. Like in this equation here. In this equation, some people pointed at the stronger acid, sulfuric, but the weaker acid, they were pointing at calcium sulfate. Calcium sulfate's not the weaker acid. Or they were pointing at water. Water's not the weaker acid. Do you know what the weaker acid is in this reaction? You have 2 choices. You can point either at carbonic acid, but I don't want to see carbonic acid unless it's decomposed. Or you can point it at carbon dioxide. Carbon dioxide is the weaker acid here. Carbon dioxide is significantly more acidic than water. And so point at that. All right, these are all examples of double replacement reactions. And so we're going to do a demo lab today. The demo lab is going to be experiment 17, the reactions, which is part 3 here. So we did the electrolytes for experiment 17, and then we moved on to redox reactions. Now we're going to go back to double replacement reactions. So what you're going to do is we're just going to take our observations here. I use nitrile gloves. Nitrile gloves have good chemical resistance. Nitrile gloves and a lab coat. I have a lab coat, but I couldn't find it right now. I don't know where I put it. Are required now. So at UCLA, you have to have a lab coat and gloves. There was a lawsuit, and actually, not just a lawsuit, but there are criminal charges. So everything's gotten a lot more strict at UCLA. All right, so what we're going to do is we're going to take some lead to acetate. So I want to wear gloves for lead. It's a heavy metal. So this is my solution of lead 2 acetate. You write the observations below here. What would you call this? Yeah, clear colorless solution, or CCS. CCS is a standard abbreviation for clear colorless solution, so CCS is fine. Now, there are 2 types of stoppers. This is called a reagent bottle. It's a chemical reagent. And we have a stopper with a little fin on the top. These stoppers are meant to be held between your fingers, and so you can hold the stopper and hold the bottle with one hand and hold the other thing with your other hand. So I'm going to get my beaker here, and then I'm going to pour this. So one of the safety rules for this, one thing is we don't set the stopper down, especially right side up like this, because that could lead to contamination of the stopper. This is a ground glass stopper, and so when you replace it here, we can contaminate the solution. It's best not to allow it to touch anything. But one of the safety rules is we always grab the bottle, the reagent bottle, from the label. Because what happens is you get drippings. And if you look at the drippings here, do you see they dried up and left a white, you know what that white coating is? Solid lead 2 acetate. So I'd rather not touch that stuff. All right, and then sodium carbonate. When I look at sodium carbonate, this reagent bottle has a different stopper on here. It's also a ground glass stopper, but it's a flat top. This one I can't hold between my fingers. This one's designed to be removed and then placed upside down on the bench top. Don't put these right side up. Every semester I see people put these right side up on the bench top, because whatever contaminants you have on the bench top will be transferred to your reagent here once you replace the cap. So we don't. And the same thing here. You see there was some dried up spills on the outside here. So we grab it from the label end, and then this we'll just set down on the bench top, and then I'll fill my beaker with some sodium carbonate. I don't need that much. Am I recording? Let me make sure. Yeah, recording this. So what order should I do it? Should I put in the lead carbonate first or the sodium carbonate, or does it matter? It doesn't matter. So I'm going to just put some lead 2 carbonate, or not carbonate, acetate, lead 2 acetate in here. And then I'm going to get my beaker of sodium carbonate. And then let's see what happens. I'm going to add the sodium carbonate to the lead acetate, and do you see that? What did we get there? A white precipitate, a cloudy white precipitate. It's pretty thick. It's going to take some time for it to settle down. But it's already starting to settle. Once this settles down, then what we're going to be left with is a clear liquid layer on the top, clear colorless, and precipitate on the bottom. It's just going to take some time. So what forms here is a white PBT and a CCS. The CCS is starting to show up at the top. What can I do to help speed up the settling? Because some of the crystals are quite small and might form a colloidal suspension. And one way to get rid of a colloidal suspension is by digesting. How do you digest it? Digesting means not like physically digesting. Digesting means clumping up the tiny crystals into bigger crystals. Put it on ice will decrease the solubility. We do something else though, because if you put it on ice, it slows the motion down. So the clumping actually kind of slows down, but the solubility decreases, so we'll maximize the amount of precipitate. So we often put it in ice to maximize the amount of precipitate. But to get bigger clumps, we need the clumps to come together, to crash into one another. And so what did we do for barium sulfate? How did we digest the colloidal precipitate of barium sulfate precipitate? You heated it. Remember we heated it? So one thing I could do is I could just put this in a boiling water bath and let it digest, and then it should settle down. But it's settling down slowly. You can kind of see it there. Do you see it? What I'd like to do is I want to do number 15 next. Number 15 is HNO3, nitric acid, to precipitate from number 1. And so what I'd like to do is I'd like to decant the liquid layer. You know what decanting is? Decanting is just pour off the liquid layer and leave the precipitate down there at the bottom. So I'm going to let this settle. The other way we get this to settle more quickly, 1, digest it with some heat, or 2, we can centrifuge it, or 3, we can filter it out, or 2, it doesn't matter, 2, 3, whatever. Maybe I'll try to digest it a little bit. So when I heat this, I don't want to point it at me in case it bumps, and you shouldn't point it at anybody else. And then we heat it on the soft part of the flame up here. Gently heat it a little bit. I don't want to boil it though. Do you hear that? Starting to boil. So this is good because I'm holding this in my hand so I can move it away. So either you hold the burner in your hand and move it away as it gets too hot, or you hold the test tube and move it away as it gets too hot, or both. You can do both. All right, that wasn't, I need more digestion here, but it is getting a little bit clearer. It's clear enough for me because there's always a compromise between maximizing yield and saving time. We can maximize yield, but it's going to take too long. And so this is clear enough. I'm going to decant most of the liquid layer off. I'm just going to use a stir rod here to guide the liquid down. So I got most of the precipitate there and some of the liquid layer off. Okay, so now I'm going to add some nitric acid. And so nitric acid, what's your observation for nitric acid solution? CCS again. And this one does not have a ground glass stopper. You see, this is just a plastic stopper. So I'm going to remove the plastic stopper and I'm going to pour some nitric acid in this one. And then just replace it. Some solutions we don't use glass stoppers. Sodium hydroxide is one of them. If you use a glass stopper on a sodium hydroxide solution, it welds the stopper to the glass bottle. Sodium hydroxide etches glass. All right, so let's see what happens. Now, it makes a difference. Have you ever heard the safety rule AA, double A? Yeah, add acid. Okay. Giovanni knows. You add acids. You always add acid because it allows you to control the reaction better. Like I can control the heat, and when it starts to get a little bit too hot, what do? I remove the heat quickly. And the same thing with acid. We add the acid so we can better control it. because when we add the acid, we can just add a drop of acid and see what happens. Whereas if you dump this into there, you could add this slowly into the acid, but you got too much acid there, and it could lead to a violent reaction. And so here it makes a difference. We always add acid, not the other way around, and then we add it slowly to make sure it doesn't go too violent. You see that? Did you see all the bubbles? What do you call it? Bubble formation like that? Effervescence. So we got some effervescence going on, and it's generating a gas. And the gas is a CCG. It's hard to control this. If I had a dropper, it'd be easier to control. There we go. And so we don't want the reaction to become too violent, but basically what happened to the white PBT? It's completely dissolved. So white PBT dissolved with effervescence, CCG formed, clear colorless gas, and we're left with a CCS. Oh, actually, there are some crystals left down there. Let me try to get those. So two ways that we mix. One, you could swirl the test tube. Two, another way is to tap the bottom of the test tube with your finger. And a third way of mixing is to use a stir rod to mix it. And so those are different ways of mixing. Okay, did you guys get that observation? All right, what's next? Actually, we're going to go across. So we're going to do lead-2 acetate with sulfuric acid. So let me get my sulfuric acid. And so what would you say for sulfuric acid? CCS. And let me pour some sulfuric acid in here. So what do? Do I add the acid or do I add the other stuff to the acid? So I have the lead-2 acetate. Should I add the lead-2 acetate to the acid, or should I add the acid to the lead-2 acetate? You always add the acid. And we want to be careful. We want to do this slowly. Because when you add, especially sulfuric acid, when you add sulfuric acid to water, it gets hot. Sometimes it gets so hot it immediately starts to boil, or you can have a little mini steam explosion. If you have a little mini steam explosion, what happens is concentrated sulfuric acid can shoot out of the test tube and land on your arm. That's actually happened before to a student. So what we're going to do is we're going to add this slowly. Oh, do you see that? That's not that hot.
How fast does the temperature have to change by like how much in order for glass to break? Depends on the spread.
It depends if you're heating or cooling.
Oh, really?
Yeah. Thermal shock is usually when you cool too fast. Yeah. It doesn't have to change all that fast. If you have a hot piece of glassware like this and you put it in ice, it could crack it. It depends on what type of glass you're looking at. This is Pyrex glass. Pyrex glass is pretty tough, and so this can withstand a lot of thermal shock. We have another glass that's very common in labware, and it's borosilicate glass. Borosilicate glass is worthless with thermal shock. It's so easy to break. Oh, so we got a white precipitate. If I let this white precipitate settle, I have a CCS above it. White precipitate's already settling. We're going to do a bonus reaction here. And so write number 16 here. And what we're going to do is we're going to take HNO3 and we're going to add that to precipitate number 2. Actually, do you see it settled pretty well? So if that's settled pretty well, I'm going to decant this. I didn't have to digest it. So I'll decant the top layer and then just add some nitric acid to the bottom layer, which is this precipitate suspension. And let's see what happens. I'm going to add the nitric acid slowly. Check the heat. I don't want it to get too hot. It's not. It's dripping. You see anything happen? No, nothing. Nothing happened. We could wait, but I'll tell you it's going to be NR. No reaction.
How long do you generally have to wait for something that nothing's gonna happen?
Like 5 minutes, sometimes more. But I'll tell you, there's something else that smells here. Not useful. You have to be careful because sometimes nitric acid can generate NOx, and NOx are kind of toxic. So nitric acid must have mixed with something here because I smell some NOx.
Well, what is NOx? Noxious gas?
Noxious gas is one, but NOx are NOx.
Oh, it's like NO, whatever.
NO whatever.
You
Right?
shouldn't breathe those.
What's that?
And you shouldn't breathe those.
You shouldn't breathe those. You shouldn't breathe NOx and you shouldn't breathe SOx.
Sulfur, something oxide?
Yeah, oxides of sulfur. Both of those are poisonous. This is from this morning, so I probably shouldn't even done this. I just make, or it could be from my waste beaker. You know what? I'm gonna dump my waste beaker.
Over here.
This is the waste from somebody else's class. So I have the waste from this morning. I didn't dump it. You know, when you smell chemical, you're not supposed to smell chemicals unless you know it's safe. But you know, if you do smell, you're supposed to waft the vapors to your nose. Don't put your nose directly under it. What's that?
Which ones are you supposed to smell?
Basically none of them. But we're going to smell a couple of them. Not you, but I'm going to smell a couple of them from this lab. The best smelling chemicals are usually esters, if you like fruit. You know. So in organic, we made synthetic banana smell. This is an ester. But strawberries have a smell with esters. You can make that. I mean, it's the actual. It's the actual smell, but it was just synthetically made rather than extracted from bananas. That's why. Those are good smelling. But most chemicals in the organic lab stink. So normally at the end of the organic lab, if I didn't have a headache, then it was good. But usually I had a headache after the lab. Just didn't like the smell. It's funny. I went to work in one of the smelliest labs.
You have to explain that. What does that mean?
Which is a lab that made a lot of sulfur-containing compounds. In the Guinness Book of World Record, they have the smelliest compound, and it's what they call a thiol. And I used to work with thiols all the time. In fact, one of the other people in the lab accidentally spilled a drop of thiol onto their brand new, very expensive tennis shoes. And He spent about a week trying to get rid of the smell. You know, he tried bleach, tried so many different things, and finally just threw them away because they smelled too bad.
Qualitatively, what does it smell like?
Skunk. Skunk
How
odor.
it is.
Skunk odor styles. Skunk odor, but some of them smell even nastier than skunk odor. Bleach usually works well at neutralizing a lot of these. All right, so we're going to number 3. And sodium hydroxide you've seen before. But you should record it nonetheless. Sodium hydroxide is a CCS. So we'll take our lead 2 acetate and sodium hydroxide, and let's see what happens. And again, we get another white precipitate here.
Does adding the base have the same level as the acid?
Yeah, it depends. It depends, but to make things simpler, you just have the AA. And when we have a strong acid and a strong base, then we got to be careful. Now, it's a rule, so sometimes rules are violated. So, for example, in your titration, did you add the acid or did you add the base? We added the base, and then there you have a violation of the rule. But the rules are just, you know, of course we can bend the rules once we know what the purpose of the rules are for. And the purpose of the rules are to prevent violent reaction from occurring. And if you're using very dilute base, 0.1 molar is very dilute, and very dilute acid, which is about 0.1, 0.08 molar, then we don't have to worry. It's just when we're using the more concentrated stuff. The more concentrated stuff would be like the 16 molar, 18 molar, 12 molar. That causes trouble.
How is that? What is it called? Phenolphthalein? The stuff that makes it invisible. What is that called?
Phenolphthalein?
Phenolphthalein. Yeah. How does that? Is that a complicated reaction? How does it know?
How does it know?
Yeah.
Phenolphthalein is also an acid. But the interesting thing about phenolphthalein is in acid it's one color, in base it's another color. So it's a colorless acid, but when you remove the proton of phenolphthalein, it turns to pink or red. Yeah. It's weird, but it's just one of those things. All right, so I have the white precipitate here. And then I'm going to do a little bonus reaction here. So we'll make this number 17. And so what I'm going to do is I'm going to add some nitric acid to my precipitate and see what happens. My precipitate is disappearing. Do you see my precipitate's disappearing? I haven't even added it. So what I'm going to do is I'm going to add some more sodium hydroxide to try to generate more precipitate. And when I add more sodium hydroxide, my precipitate has completely disappeared. And so I'm going to add some more lead 2 acetate to this to regenerate my precipitate. And so what happened was I added a little bit too much sodium hydroxide. Too much hydroxide causes a competing reaction to occur. That competing reaction we'll talk about in Chem 1B. I'm not going to talk about it much. So now I got lots of, or do I have lots of precipitate? Yeah. I have precipitate here. Add a little bit more lead 2 acetate. Okay, now I have it. So I have lots of white precipitate here, and now I'm going to add my nitric acid to this. So this will be for box 17. Nitric acid plus a precipitate from number 3. Let's see what happens. I'm not going to decant this because it can take too long to settle. Do you see what happens there? Do you see the steam coming off? There's some steam coming off there. It's warm. Test tube's quite warm. But we added the acid and the precipitate was completely dissolved. No effervescence though.
How do you tell effervescence from just steam from the heat?
Bubbles. You'd see bubbles of gas forming in the liquid itself. Whereas the steam's just coming off the surface.
So champagne's effervescent, but dry
Yeah.
ice is something else.
Yeah, right. Dry ice is sublimation. All right, so now I have some aqueous ammonia. So this is what aqueous ammonia looks like. What would you call it? CCS. Aqueous ammonia contains a little bit of ammonium and hydroxide. So a little bit. It's like 99% ammonia, 1% ammonium and hydroxide. But that little bit of hydroxide can react with lead ions to form a white PPT. Do you see it? Is there very much PPT in there? No, not as much. I'll add some more ammonia. No, not much PPT, but we do get some PPT. Now, ammonia has a very powerful odor, and I can smell it. It's very strong. I mean, if I put this under my nose, I could pass out, but this is okay. Yeah, some people. It clears your nasal passages pretty well. Smelling salts, you
I
know.
was gonna say, I thought that
Yeah.
that was like wakes people up from passing out, so I was confused that it could do the opposite.
Well, I guess it wakes you up. Maybe smelling salts. Is smelling salts
That's what people do, like hockey players use them.
okay? The smelling salts, yeah. So I have it backwards then. But anyway, I got a little bit of precipitate in there, lead 2 hydroxide. And for box 18, we're going to add some nitric acid to this and see what happens to the precipitate. The white precipitate from number 4.
Oh, the Adobe is projecting. The Adobe symbol is projected on our side of the vial. So I thought some crazy stuff was happening.
All right.
Wacky.
Wow, do you see all this?
Yeah.
That's smoke. That's not steam, by the way. That's ammonium nitrate, solids, crystals forming in the air above it. But this is it. Let's see. I'm going to stir this.
Is that vapor on the top or is that a liquid?
Let's precipitate. I'm going to mix the precipitate in with the acid. The precipitate was just floating at the top. And so now I mixed it with the acid. So the precipitate was dissolved by the acid. All right, let's go on to number 5. What's that, number 5 called? Iron 3 nitrate. In some old bottles, you'll see it labeled ferric nitrate. Ferric for iron 3, ferrous for iron 2. This is an old bottle. Didn't bother changing the label. But let's take a look at what it looks like. So this is what iron 3 nitrate looks like, or ferric nitrate. And how would you describe that? Yeah, like a clear orange solution. Maybe COS or something like that. So I'll pour some into the test tube. And then I'm going to add some sodium carbonate to this. And let's see what happens here. Do you see that? Did I form there? A brown precipitate. So you got a brown precipitate, and then above it will be a CCS if I added enough sodium carbonate. So brown precipitate. This one you don't have to write down the observation for because there's no box for it. But one of the reactions of all carbonates, carbonates plus acid yields, what does it yield? Carbonate and acid yields effervescence. Right? Because the acid is going to form carbonic acid, and the carbonic acid is going to decompose into CO2 and water. So I'm going to add the acid. Let's see what happens when I add the acid. Ready? So you got some effervescence and the precipitate dissolve. Now, we didn't really get that yellow color back of the, or the orange color back. There's still iron 3 in here, but it's quite a bit more dilute. And also the pH changes the color. And so this kind of color change is more of a physical process, not a chemical process. And so the iron 3 is in there, and the color is very faint. It's hard to see. But iron 3 gives it this color. Nitrates are colorless. Number 7. So we're going to take iron 3 nitrate and add some sulfuric acid to this. Or 6, yeah, sorry. Number 6, with sulfuric acid, let's see what happens. Do you see what happened? There's no precipitate, but what happened to the color?
Clear.
Yeah, it's colorless now. And so did a chemical reaction occur? Not really. This is either one, dilution, but would you expect the color to fade that much? I just did about a 1 to 2 dilution. No. And so the color of iron 3 in solution is quite dependent on the pH of the solution. The pH is the acidity, and I made it a lot more acidic with the sulfuric acid, but no chemical reaction really occurred here. And so we'd say NR.
When you get opacity, do you always assume that there's precipitation?
Yeah.
No precipitation.
Yeah, whenever it goes opaque or you can't see through it, then it's definitely a precipitate because those particles are big enough to block light. All right, now we're on to number 7. Number 7 is iron 3 hydroxide with, or nitrate with hydroxide, sorry. So let's see what happens here. Do you see that? What did we get there? Yeah, like a rust-colored precipitate, or orange, red precipitate. This is the hydroxide. This precipitate is iron 3 hydroxide. You don't have to write that down in the observations here. We're going to do that for the equations. But let's see what happens when I take this hydroxide and mix it with acid. And so I'll get some more nitric acid. And what do you think is going to happen to this precipitate when mixed with nitric acid?
Stir it more.
Yeah, I need to stir this. So different methods of stirring. 1, tap this with, these big test tubes are hard to tap. 2, swirl it. 3, just use a stir rod. I'll use a stir rod. And so all the precipitate dissolved. Actually, there's some flecks of crystal there, but those will dissolve eventually. It's quite warm. This test tube's very, very warm. All right. You don't have to write what happened with the acid. Now we're going to go back to ammonia. Ammonia is a small concentration of hydroxide in here. That sodium hydroxide had a high concentration of hydroxide. This is a low concentration of hydroxide. Let's see what happens here. But even with this low concentration of hydroxide, we still get a lot of precipitate there. You see that? And so this is another rust-colored or orange or red precipitate. We ran out of nitric. Okay, so we'll try this again. This is just a bonus reaction. You don't have to take observations for this one, but I'm going to take this rust-colored precipitate and add some acid to it. See what happens here. Stir it up. And see all the precipitate dissolved.
The test tube heat up again, or?
Yeah,
Oh.
test tube is warm. What's it? It's exothermic. Mhm.
Write that down as an observation.
No. Because we don't know if that's from the reaction or from the acid mixing with the water. All right. Number 8B. Ammonium acetate and sodium carbonate. They have nothing here because there should be no metathesis reaction. If you take ammonium acetate and sodium carbonate, what we expect to form is ammonium acetate, not ammonium acetate, ammonium carbonate and sodium acetate. Sodium and ammonium salts are all soluble, so there's no precipitate. None of those decompose into gas, and we're not going from a stronger acid to weaker acid, so there should be no reaction. However, I'm going to do it anyway because ammonium is an acid. It's just a weak acid. And acids, what do they do to carbonates? They make them effervesce. And so I'm going to try to get this to react. So I'm going to take my ammonium acetate and mix it with sodium carbonate and see if I can get some effervescence. So this is ammonium acetate here. It's a CCS. And let's add that to the sodium carbonate. Okay, let's see if ammonium is strong enough or concentrated enough to react. And I see no effervescence here. That's with ammonium acetate. Ammonium is an acid. It's on the weaker end of the acid chart. Let's get a stronger acid. I'm going to try nitric acid. So I just added ammonium. It wasn't strong enough. We'll try nitric. Do you think it's strong enough? Let's try it here. Yeah, it's strong enough. So this is why you want to add the acid, and you add it carefully, you know, because it could easily react more violently than you expect. And so that's it. So we get some effervescence there.
For 8B.
What's that?
For 8B.
8B, yeah. No, 8B is no reaction. No visible reaction here, 8B.
Oh, this is the bonus variant.
Because, yeah, it's a bonus. I just, the ammonium wasn't strong enough. It didn't cause it. Yeah. Let's go to 9. Ammonium acetate and sulfuric acid. Ammonium acetate. Here it is. So what should I do? Should I add the ammonium acetate to the sulfuric acid or add the sulfuric acid to the ammonium acetate?
Sulfuric acid.
Yeah. So I'm going to pour the ammonium acetate in here. And ammonium is a weak acid, but acetate is also a weak base. And so I expect something to happen here. So I'm going to take my sulfuric acid and add it slowly to make sure. It's like the heat. You just check it to make sure it doesn't go violent. It doesn't look like much is happening. And the temperature isn't changing much. But doesn't smell that great. You know what smell I'm supposed to smell here? Vinegar. Ammonium acetate doesn't have any vinegar smell. Sulfuric acid has a corrosive smell. I don't want to smell it. But it's probably the sulfuric acid I smell.
Can we do volunteers?
But this is okay here. So a little bit of vinegar smell to this. Not much heat.
Do you think if we heat it up, there'll be more of a reaction, or
There'd be more of a smell.
no smell?
Yeah, it'll drive off the acetic acid. Acetic acid forms in this reaction. So the products of this reaction are acetic acid and ammonium sulfate. Ammonium sulfate doesn't have a smell. And so this is where you might smell the reaction.
Maybe when you write down the smell as an observation.
Yeah, the smell would be an observation. The vinegar has a very characteristic odor that most people can recognize. So we're going to do ammonium acetate and sodium hydroxide. Here I'm going to violate the rules. And so, the add acid, it's just to keep things simple. But here we could just add this slowly. Sodium hydroxide is a strong base. We'll just add it slowly. I don't see much happening. I can't really feel much difference in temperature. But I'm going to smell this one. This one is going to smell like, not vinegar, it's going to smell like ammonia. This one smells like ammonia.
I think that's not additional too much ammonia.
I think so. I mean, this is why this one has a lid on it. This is the only one with a lid on it because otherwise you're going to start to smell the ammonia if I waft it towards you guys.
Decide whether or not a reaction is safe to smell if they've never done it before. Like, oh, I don't know what this is. Are they gonna like not smell? Are they gonna put a spectrometer? Are they gonna have like someone they don't like smell? Like,
It's
what's the
called
procedure?
survival of the fittest.
Yeah. There's certain smells that you run away from. One is rotten egg smell,
Really, what's that?
hydrogen sulfide. And another one is burnt almond. Burnt almond, you run away from that.
Oh, it's cyanide, right?
Yeah, cyanide.
I feel like it's not nice. It's probably too
But there's others.
When we were like discovering, actually answer
It's like you shouldn't mix certain things like, if,
that. Which is great.
like if you burn ammonia in a flame, there's a potential for making hydrogen cyanide
Really?
as well as NOx. Yeah, so you got to be careful.
Oh.
Yeah, so if this is ammonia cleaner, I'm not going to be spraying this into the flame. Okay, we're going to go on to, that was what?
That was
10? Okay, so we're going to go to 11. Ammonium acetate and ammonia, what do you expect to form? So what we're going to do is we're going to treat ammonia as if it were ammonium hydroxide, right? And so if we do ammonium acetate plus ammonium hydroxide yields what? Ammonium acetate plus ammonium hydroxide yields what? Well, it yields ammonium hydroxide and ammonium acetate. Is there any change? So number 11 is a no reaction. I don't know why they left this one blank and they didn't leave this one blank. Nothing's going to happen. So we're going to move on to 12. 12 is sulfuric acid and sodium carbonate. So I'll pour some sodium carbonate in here, and then I want to do what? Add the acid or add the sodium carbonate? I'm going to add acid. And I'll try to do this carefully, but let's see what happens here. Okay, so it didn't overflow. Oh, it did overflow there a little bit. But, there we go. So we got a CCS and effervescence with a CCG. And that's to be expected whenever you mix acid with carbonates. How about sulfuric acid plus sulfuric acid? No reaction. Sulfuric acid with sodium hydroxide. Now, here's where we want to be careful. Because sodium hydroxide is a strong base, and sulfuric acid is a strong acid, so let's do this one carefully. So I'm just going to add it slowly. And so this is about as violent as it's going to get. Although, you know, this is what we call dilute sulfuric acid. If I use concentrated sulfuric acid and concentrated sodium hydroxide, it's going to be dangerous. But did it look like much happened? No. But you know what? The test tube is very hot. And in fact, I don't know if you can see it, but there's steam. And the steam is condensing on the inside wall of the test tube. Sometimes as it gets too hot, you can't even hold it with your fingers. It's that hot.
So we would say heat.
Heat. This one definitely is very exothermic because it doesn't look like anything happened. We've got a CCS plus a CCS yields a CCS, but lots of heat, some steam coming off.
What was that? So sorry.
Number 13. Okay, the final reaction here is going to be number 14. And that's going to be the weak base now. So the weak base shouldn't react as violently. So I'm going to put some ammonia in here. And then I'm going to add my sulfuric acid. And so let's see what happens here. Looks like nothing happened. Ooh, it's very hot. The test tube is very hot. There's steam coming off, and it's condensing on the surface. And it pretty much killed the ammonia smell. There's no more ammonia smell to this. Ammonium has no smell. Ammonia has a very distinct odor to it. All right, so the next part of this is this. You're going to write the CE, the IE, and the NIE for each of these reactions and the driving force.